For SVM, you have linear kernel that you need to use. So SVC kernel is equal to linear, okay, and in that you have a parameter called C, capital C. So try that for various values of C. Maybe small values, say 0.001, 2. Let's say up to, so increase in multiples of tens. So 0.001, then 0.01, 0.11, 10, 100, all these, and see which is given the best score. Okay, so yeah, we briefly did SVM. Okay, I showed you the code and all. So before that, you have to basically handle the text data that is given to you. Okay, so you have to do some pre-processing, some normalization or standardization. So try them all and see, and maybe you have to do some stemming and some other things. Just look at what you can do with the text to get the good results. Okay, it's not like otherwise you just look at the code that I've already provided for clustering and classification and just copy the code. Okay, but before that, in the data itself, you have to do some pre-processing. Okay, so look at what are the different pre-processing you can do with text data. Okay, and then go ahead. Okay, so I'll tell you some of the pre-processing. Something is called stemming, is very normally done. Okay, stopwatch removal is done. Okay, and there's also one more thing that is available in scikit. That is called min-df. When you do count vectors, count vectorization. The count vectorizer has this min-df. So if a word is not present in, say, in at least 2 documents, don't consider it, or 3 documents. Okay, so minimum number of documents that a word must be present in to be considered further. Okay, so it is not important. Stopwatch removal, stemming is there. Okay, so there is a porter stemmer that you can use. All these things are available online. You can just look at it, look at the tutorials, and add those lines. There's some few lines there add. Okay, and these are all individual assignments. Yes. Okay, these are all individual assignments. I will check that all the assignments they are unique. Okay, so don't try to copy. I have mentioned it in the assignment problems also. Yes, you have to do only one problem, either classification problem or the clustering problem. Okay, just to keep it simple for you, I have done that. Okay, the last time I used to give both, but this time I am giving only one. Okay, only one, but more classifier or more clustering in a single one. So do whatever you find easy to do, or whatever you are thinking, you think that you can get good results. Okay, so do only one problem, either clustering or classification. Okay, and you have a lot of time. You have 2 weeks till 28th. Deadline is 28th, so you can submit till midnight of 28th, and so best of luck in that. Okay, and the quiz will start tomorrow morning. Okay, for that also you'll get like 10 days. So till 24th midnight, 11:59 or 11:55. Just check the deadline. It will be available. And if you have further doubts in assignments, yeah, you can discuss in the forum. Okay, don't wait for the class, next week's class. You can just send me a question or just open a new discussion topic in the course forum. Okay, so I see this time almost there is nothing, no discussion going on there. So it doesn't look good. It seems like you are not interested to learn more about the something outside that whatever discussed in the class in the contact hours. Okay, so if you discuss something in the forum, that makes it look like you are interested to learn more about it. Okay, so that's why I'm giving something different that we have not done in the class exactly. Okay. So there's another question. So in nutshell for clustering, we did all emails into a data set, perform data analysis for all words, and perform clustering. Yes. Okay. And what you can do is for both clustering and classification, what you can do, you can use TF-IDF. Okay, you can use TF idea for weighting each word. To give weightage to each word, you can use TF idea. Okay, rather than just using count. Okay, and one more thing that you can do is, instead of using raw count, try to use log base 2, obviously log of base 2 of the count of each word. Okay, only thing here that you have to keep in mind is that if the count of any word is 1, okay, and then in a document, then the TF of that will be 1, right? The term count will be 1, and if you do log of that, log of 1 will be 0. So to avoid that, just add 1 to term count for every word in a document. Okay, so that log 1 will be log 1 plus 1, that is log 2, so that will be 1. Log 2 will be log of 3, base 2, and so on. Okay, so log 1 plus term count. So you can add 1 before performing log. Okay, so I have seen the logarithm of term count actually gives better score than raw term count. Okay, apart from that, the IDF it's also available in scikit-learn. Okay, you can use that directly if you wish. It's up to you. Okay, there's a question: is there any structure for assignment? What kind of structure? No, there's no structure. Just solve them, create the output file, your code, put them all in a single file, zip it, a single folder, zip it, and send it to me. Upload it. Okay, so I'll create one folder where you can upload the assignment. Okay, yeah, code and all, just put them all in PDF. Okay. I don't know whether you can create a snapshot that will make it easier for me to check that you're not copying from each other. Well, let me just check whether when you run a code, what happens? Idle. Okay, it doesn't show you. Okay, so just create a PDF file of your Python code, or any other format is also fine. Okay, if you just want to send a JPG file, just take a screenshot of the code if you can in a single page. And for the outputs, yes, whatever you want, a screenshot or JPG image, but put them all in a single zip file. Okay, don't send me multiple files, only one file per student. Okay, so that's about the assignment, and quiz will open tomorrow morning. Okay, make sure to attempt it before the deadline. Okay, this time I will not give any extension to anyone for any reason, so try to finish it within 1 week so that you don't rush through later and then forget to attempt it. Okay, so we were looking at clustering. So we did 2 clustering in the last couple of sessions. One was the k-means clustering, and the other was the hierarchical agglomerative clustering, that is the bottom-up clustering. And we looked at one measure, one metric to evaluate how good our clustering is. So that is called that was called slow weight coefficient. Okay. So in this you look at all the clusters, okay, and then you try to find out the cohesiveness and separation of the clusters from each other and within cluster, okay, cohesion within a cluster, and the separation of various clusters, so A and B, and based upon A and B you calculate the slow weight coefficient. Okay, so that's called internal measure. The reason is that you don't require any other information apart from the clustering that you have performed. Okay, so clustering that has been done is the only information that is required to calculate Slevit coefficient, and hence it is called internal. Okay, apart from the Slevit coefficient or this internal measures, there are external measures that can be performed, or external evaluation measures which could be calculated or computed. So these external measures, they actually require information about the classes which are existing. Okay, so each example or each sample may belong to a particular class that you know. Okay, it belongs to a particular class, and how well the clustering has been performed, knowing the class. Okay, so that if you use the class information as gold standard, okay, and then base your results on the existing knowledge of that classes that you know each point belongs to, then you have what is called external measures. Okay, now because you now know the class of each sample, but you are not using that knowledge of the class to create the clusters. But once the clusters have been created, to evaluate them, you know, now use the knowledge base of the classes, and then you compare whether class by class or some pair by pair and so on. So there are multiple external measures like this. We'll discuss a few of them. Okay, most of them are very easy. One of them is a bit more involved, so I will discuss in detail all of them. Okay, not all of them, but 3-4 of them. Okay, let's come to this example. So it will be clear from the example what is meant by external evaluation. Okay, so let's say you have done some clustering, and these 6 clusters have been created as a result. Okay, so these are the 6 clusters which have been formed. That is 1, 2, 3, 4, 5, 6. These are the numbered cluster. Let's cluster number 1, 2, 3, 4, and 5 and 6. Okay, but here remember our iris data set example. Okay, what was that data set? You know that there are 3 species of flowers. Okay, and then you are clustering without considering that class, we are clustering those 150 examples, looking at the 4 features, that is sepal length, sepal width, petal length, petal width. Only 4 features were considered, and then you try to group them into say 3 or 4, whatever number clusters, or 3 clusters, let's say, and then compare those 3 clusters that you've got with the original class. Okay. So if you compare with the original class and then decide on the accuracy of the cluster or the goodness of the cluster, then it's called external measure. Okay, so you know the classing to begin with. Okay, it's not always possible, but if it is there, if you want to evaluate, say you have come up with a new clustering algorithm that you think is very good, but if you want to show that it is how good it is, then you have to use some already existing data set which is labeled, and then show that without looking at the labels, your clustering is giving you a good result. That is, the clusters have one-to-one mapping with the existing labels. Okay, now here the existing labels are these 6: entertainment, financial, foreign, metro, national, sports. So let's say it's most likely you are labeling documents, okay, about news items. Okay, and these news items have been taken from these 6 categories: entertainment, financial, foreign, metro, national, and sports. So these are the 6 categories that you know that, and you know each sample that you are using that belongs to each category. You know that. Okay, but then each of these document has words as features, okay, and various features you can create yourself. Then you create your 6 clusters without knowing which class each one belongs to. Okay, so while creating clusters, you don't use that information, that category information or the class information, just like we did in iris data set. When you clustered them, you didn't use the label, column label, right? So here you are not using entertainment, financial, all these labels. You are not using all these categories. Okay, but you just tell the clustering algorithm that you want 6 clusters to be created, and it creates those 6 clusters. Okay, and these are the the distribution of those these documents in each cluster. So cluster 1, you can see that it contains. So after the clustering is done, then you look at each sample and you decide, and then you look at the original class, and then you say that okay, in the cluster 1, 3 samples were actually from entertainment, 5 are from financial, 40 are from foreign category in the original label dataset, 506 are from metro, and 96 are from national category. So these are the 6 categories, and 27 are from sports. So these are the 6 categories that the first cluster contains documents from. Okay, so these are the documents in cluster 1, and those documents are from these categories. So they are not all from the same category. So of course the cluster is not pure. If all the documents in a cluster are from the same category, then you say that the cluster is 100% pure, or purity is 1. Okay, so in this case, okay, one more thing, the majority example in any class represents that label. Okay, so in the cluster 1, since 506 items or 506 documents, they belong to metro, that is majority, right? So 506 is the majority. So you assume that cluster 1 maps to metro label. You assume that. And similarly, cluster 2 will map to foreign label. And what will cluster 3, 4, 5, and 6 will map to? Just tell me. Cluster 3 will map to which category? Cluster 3 is sports. Cluster 4 is financial. Cluster 5 is entertainment, and cluster 6 is financial. Okay, so these are the majority in each cluster. So you just map them one by one by hand. Okay. Now you remember that you are using the existing labels. So that's why these are external evaluation, because now whatever we are calculating is taking that information into account. Right. Okay. Now the question is calculate entropy and purity. So let's say you want to calculate entropy of cluster 1. Okay. So entropy, if you remember, it is minus P log P for all, or it's minus Pi log Pi, where Pi is the probability. Pi is the probability. So Pi is the probability of each kind of class. So what is the entropy for cluster 1? So for that, just look at all the documents in cluster 1. So there are 3 documents that belong to entertainment class. Okay. 5 documents belong to financial class, and so on. Okay, so what is the sum of all this? Maybe I open the idle. So 3 plus 5 plus 40 plus 506 plus 96 plus 27. So the sum is 677. That's also given, I think, in the, yeah, no, it's not given. So the sum is 677. So these many documents are present in the first cluster. Okay. So out of these 677, 3 are from the entertainment category. Okay. So the probability of this particular label called entertainment in this category is 3 by 677. Okay. So 3 by 677 is the probability of entertainment category in cluster 1. So that is probability. So P log of 3 by 677 minus of that. Okay. So that is just keep minus outside and then sum them all. Then next is 5 by 677 log, so all log in base 2, log base 2 of 5 by 677 and so on. So sum them up, all the categories. So finally last is sports category, that will be 27 divided by 677 log of 27 divided by 677. So remember that 677 is the sum of all the documents in the category in that particular cluster. So we're looking at cluster 1. Remember we are looking at cluster number 1. And how many documents are there in this cluster? 3 plus 5 plus 40 plus 506 plus 96 plus 27. So that is 677. Okay, so 677 is the sum of all the documents in cluster 1. So we want to find the entropy for cluster 1. We are calculating entropy for cluster 1 here. So I'll look at cluster 1. Is it clear? 677 is the sum of all the documents in that category, in that cluster, sorry. So cluster 1. So look at row 1, that corresponds to cluster 1, you get 677. So when you solve this, you'll get the answer for entropy. Okay, so that will be the entropy, whatever you get will be the entropy. And similarly, you can calculate the entropy of the second cluster, entropy of the third cluster, entropy in the fourth cluster, fifth and sixth. Okay, you can calculate them for all. The second question is purity of each cluster. How do you calculate the purity of each cluster? Yes, log base 2. So in this entropy, you always use log base 2. In fact, in everything you calculate, we are using log base 2 only. Okay? Whenever I mention log base 2. So I've written it log base 2, I think, at most places. Only log base 2 is correct. Okay, what is the purity of cluster 1? So the cluster 1, as we have discussed, it belongs to metro. It corresponds to the metro class. Okay, so cluster 1 has, because 506 is the majority, so that 506 documents actually are from this class, from this category metro. Okay, and remaining are all noisy data. Okay, so how pure is the cluster? That is 506 divided by the total number is the purity of this cluster. It's also called precision in terms of classification. It's also called precision of the cluster. So 506 by 677 is the purity or precision of the cluster. Okay. And that you can calculate for the remaining also. Okay. So when you calculate for cluster 2, again you sum up all the documents in cluster 2 and then calculate entropy and purity. Can do that. So you get entropy of 1.22. To solve this, you finish this, you get entropy of 1.22. Okay, now if you don't want to use calculator for this long calculation, you can always write in idle. Okay, you can always use numpy. Let me just show you how you can do that. Maybe. So do I need to show you how to do that in idle, or you can do that yourself? Calculations. Okay, let me show that. Okay, you can do it yourself. Okay, fine. That's good. So for purity, we just look at the majority class. How many documents are there in majority class? There is no need to take any log. It's just the number in the majority, that is 506. So for purity, it is just the majority number divided by total. In this case, was in cluster 1, there were 677 documents. So out of that, only 506 actually belong to majority, because that cluster is represented by the majority class. Okay. So 506 are the actual elements which represent the entire cluster. So the purity is 506 by 677. Right. Okay, someone asking log base 1. No, log base 1 or log base 10. There is nothing like log base 1. Log base, no log base 10. All, whenever you are taking logarithm, it is log base 2. Okay, let's look at a few more external evaluation, the simple ones. The precision I've already told you. Precision and purity here are same. Okay. Recall of cluster. Okay. Now recall of cluster. Remember in case of classification. So these are the classification oriented measures. Okay. Precision and recall. So they are mostly used in classification, but here they are kind of fit into clustering. How to fit precision and recall in clustering, in measuring clustering. So recall here will be, so in classification, recall is out of the actual number of documents belonging to the class, how many has it been able to get as in the particular category, right? So that is TP upon TP plus FN. So in this case, it will be out of all the documents which belong to metro class, how many are in the cluster number 1. So it will be here in this case, in cluster number 1, there are 506 of this category. Okay, but in cluster 1, there are only 506. Total number of documents in the metro class, if you look at the column, total at the bottom is 943. So out of 943, the clustering could only put 506 in cluster 1. Okay, so that is the recall of cluster 1. Okay, so 506 by 943. So that's the recall. So here the precision is 0.74 after solving 506 by 677. You get the precision of 0.74. Okay, and 506 divided by 943 gives you the recall of 0.53. And similarly, you can calculate precision and recall for any other cluster. Okay, or for the entire clustering also you can do that. Now let's look at simpler cases so that the calculations are easier. Okay. Now purity of, let's look at this example. We have 3 clusters. Okay, and so because we are using external measures, so the actual class labels of each sample or each example. So the class. So there are 3 classes here. That one is represented by cross. One class is represented by circle, and the class is third class is represented by diamond. Okay, so 3 shapes are there: cross, circle, and diamond. So that represents actual class. Okay, but after clustering, you got cluster 1, cluster 2, cluster 3. So for example, in cluster 1, if you look at it, there are 5 samples which are cross, which belong to label cross. Okay, and there is one from the label circle. Okay, so individually, the purity of cluster 1 is 5 by 6, because the majority is X, 5 of them out of 6. The cluster 2, the majority is 4, circles. So 4 by 6 is the purity for second cluster, and cluster 3 the majority is diamond. So 3 diamonds are there out of 5. So the purity is 3 by 5 for the third cluster. For the second cluster it was 4 by 6. For the first one it was 5 by 6. So that is individual clusters purity. But if you want to find the purity of the entire clustering means all the clusters combined. Okay. So one simple way of doing this is just look at out of the total number of samples. Okay. So total number of samples, how many are there? 12 plus 5, 17. Okay. So there n is equal to 17. Total number of samples. Out of these total samples, how many are actually in the correct cluster? So look at in the first cluster, 5 are in the correct cluster. 5. In the second, there are 4 in the correct cluster. So 5 plus 4 is 9, and 3 in the third cluster. So 9 plus 3 is 12. So 12 by 17 will be the purity of the entire clustering. 12 by 17. So just calculate it, get the answer. That is purity of the entire cluster. That is one way of calculating the purity of the entire cluster. Okay. Okay, there is a question, why are we taking X in the first cluster and 0 in the other? Okay, so as I have explained earlier, every cluster is represented by the majority class. Okay, so in the first cluster, X is majority, cross is the majority. In the second cluster, circle is the majority. In the third cluster, diamond is in the majority. Okay, so just look at this. So the purity will be in terms of those 3 items. Okay, so every cluster is represented by the majority class in that cluster. Yes. Okay. So purity in each cluster is equal to sum of the maximum in each cluster divided by the total number of samples. That is correct. Okay. So it's easy to calculate. Okay. So the maximum in each cluster is it represents what that cluster's class is. Okay, that will be represented by the majority. Okay. Okay. Now there is a question: can we see the previous table visually? No, it's too big. Okay. For seeing visually, you need some small examples like this. Okay. So here you have 6 clusters and too many examples. Okay, to see anything visually. Okay, so when you go beyond certain numbers, in which, like in the case previous, you then use computer for those. Right? You know the tactics, you know the method. Give it the method and let it do the job for you. So the answer is 0.71 purity of the clustering. Okay. Okay. Now there is one more evaluation measure that I will discuss before the clustering is over. That is the RAND index. Okay, that is more involved, and because we have done something more involved in case of classification, we should know some advanced methods also. The RAND index is one of the more involved or more advanced example. Okay. Okay, there is a question. Recall. Can we do for this? Recall and precision. So remember they are cluster wise. Okay. Whereas purity can be like for entire clustering, but when you use recall or precision, you have to do it cluster wise. Okay, and then maybe you can do average of the clustering to get the average recall or average precision. Okay, but you cannot do for the entire clustering just like this summing and dividing. Okay, so let's look at the RAND index, that is more involved. So instead of looking at each example individually, so remember it's a bit more involved, so you have to understand it first before trying to solve it. Okay, so instead of looking at each example, here you look at the examples in pair. So example I'm calling here, it means samples or data points that you can see, cross or O's or diamonds. Okay, so each example, also you look into each pair, not each individual example. Okay, pair by pair. So there are n examples totally. So how many pairs are there? NC2, right? Simple mathematics. So if there are n examples, you can create NC2 pairs and choose 2. Okay. So in this particular case, how many examples can you? How many pairs will be there? When there are 17 examples, how many pairs are there? 17C2. Okay, so 17C2 is 17 into 16 by 2. That is 17 into 8, 136. Okay, so in this case there are total of 136 examples. Okay, so the 136 pairs out of 17 examples. Okay, so right now when you are looking at the total number of pairs, don't worry about which cluster these pairs belong to, whether they belong to the same pair or not. Okay, but now you'll calculate whether two pairs, okay, which belong to the same cluster, they are from the same class, okay, or they are from different class. So remember we are looking at pairs now. So this measure will calculate, we'll see that we'll give high score to those examples, those pairs, such that if two pairs are from the same class and they are in the same cluster, okay, they should get high score. Or you can say the clustering is good if two similar examples means they belong to the same class, actual class. Okay, if two similar examples are put in the same cluster, then the clustering is good. And also if two dissimilar examples, okay, dissimilar examples mean they are from different class. Okay, the labels are actually different. If two dissimilar class are put in different clusters, then also we say that it is good. Okay, because if they are from different class, they should not be in the same cluster, right? So if these two are good, if these two are valid, that these two are true, that similar examples are put in the same cluster and dissimilar examples are put in different clusters, then it's a good cluster. Okay, on the other hand, if two dissimilar examples are put in the same cluster, for example in the first cluster you can see that cross and O, they are dissimilar but they are put in the same cluster, that is not good. Okay, or if two similar examples are put in different clusters. Now for example here we look at cluster 1 and cluster 2, two similar examples have been put in different clusters, so that is also not good. Okay, so this is not good, this and this is also not good, that two dissimilar examples are put in the same cluster or two similar examples are put in different clusters. This is not good. Okay, what is good is two similar examples are put in the same cluster, like these examples. I'm only showing a few of them. Similar examples are put in the same cluster and different examples are put in different clusters. Okay, so these are also good. Different or similar dissimilar examples are put in different cluster. Okay, So this is good. This is good. These similar examples in different clusters. This is also good. Okay, so these are all good pairs. Okay, so any cluster which is following this should get high score, or you can say that clustering is good. Okay, and these are given some names here. Okay, so TP like for true positive, but here we are adding capital. Okay, so true positive are true means correct, as we have I have explained in classification. So true positive means they are correctly or similar examples are put in the same cluster. So for example, this will count towards a TP. This pair is counting towards one TP. Okay, then this is another pair that is one more count to the TP. So TP will be the count of or the number of such pairs which belong to the same class and they are put in the same cluster. Okay, is it clear so far? TP, what is the meaning of TP? Is it clear or not? Yes or no? So similar examples are put in the same cluster. Okay, so how many such pairs are there? So sum all these pairs so that they are in the same class and they are also in the same cluster. Count all those pairs, so that will be your TP. Okay, so let's count. Okay, just to make it clear, let's count. Let's look at cluster 1. Okay, so how many pairs are there in cluster 1? It doesn't matter which class it belong to. Okay, so how many pairs are there such that they belong to the same class and are in the same cluster? So obviously we are looking at only cluster 1 here. So what will be the count of such items? So we can see that there are 5 crosses. Right? There's only one circle. Okay, or one O. So there's obviously no pair for O. So only pairs you can make is with axes. Right? So there are 5 axes. Okay, so how many pairs can you make out of 5? 5 C2. Right. So that means 5 C2 pairs are there in the cluster 1 which belong to same class. Okay, so for example, if you look at this pair, this belongs to, this is counting towards TP. This pair is counting towards TP. This pair is counting towards TP. This pair, and all these different combinations are there. They're all counting towards TP. Okay, so how many such pairs are there in cluster 1 which belong to pair? Remember pair. Okay, so there are 5 X in this particular case. Okay, so 5 C2 pairs are there. Obviously 5 C2. Okay, so that is equal to 5 into 4 by 2. That is 10. So 10 pairs are there in cluster 1 which belong to same class. Okay. Okay, then it is not 2. No, it is not 2. Okay, meaning of TP should be clear. Okay, so TP means how many pairs of examples belong to the same class. So TP is 10 for cluster 1, but you have to look at total number of TP. So we have only looked at cluster 1. Now look at cluster 2. So how many pairs in cluster 2 belong to the same class or to similar class or similar examples which belong to cluster 2? So you can see we cannot form any pair in cluster 2 with X. You cannot form any pair with diamond, but you can form pairs with these 4 circles. Okay, that means 4 circles. With 4 circles you can make 4 C2 pairs in cluster 2. So that will be 6. Okay, so 10 in cluster 1, 6 in cluster 2. In cluster 3, how many pairs are there from the same similar class or similar examples. How many similar examples are there in cluster? How many pairs of similar examples are there in cluster 3? No, not 2 pairs. There are more. So 10 in cluster 1, 6 in cluster 2. So if you look at cluster 3, you can see that there are 2 crosses. Okay, so obviously they are from the same class. So that is 1 pair for you, or you can say 2C2. 2C2 is 1. So there is 1 pair which is in cluster 3 and which belongs to the same or which are similar examples, right, or similar pairs. Similar examples mean they belong to same class. So X is 1. So there is 1 pair which belong to X. Then there is also 3 diamonds, right? So they are also from the same class, similar. So 3 similar examples. So how many pairs can be formed out of these 3 diamonds? 3C2, that is 3C1 or 3. So 1 plus 3. So total 4. Okay. So in cluster 1, you have 10 such pairs. In cluster 2, you have 6 such pairs. In cluster 3, you have 4 such pairs. Okay. What kind of pairs? Which belong to the same class or same label. Okay. So total number of these. So TP is the total number of such pairs. Doesn't matter which cluster they belong to. Total such pairs. So total. So TP will be total of that. So TP will be sum of 10 plus 6 plus 4. So that will be 20. So TP is 20. So we will not take a break today. So I'll just break the lecture and then